Hello, this is Jacob Bandic for ME210 video assignment number 4, Impulse and Momentum. For my video, I have chosen to do the average force on a tennis ball as it hits the ground. So here's me dropping the tennis ball at my height, h1, and then as seen in the video, it bounces back up to this height h2, and here's my coordinate axis, and here is me converting my height, 5'9" to meters, because this is going to be a lot easier to do in metric units in my opinion. So using the fact that 1 foot is 0.3048 meters, we can see that h1 is 1.7526 meters, and h2 is 0.07366 meters. So what is given is these two heights, h1 and h2, as previously stated. h2 has been acquired from the observation of the video and knowing that my pants are size 31, so it almost goes back up to my waist, so that's going to be about 29 inches, which is 0.7366 meters. It is known that the mass of a tennis ball is about 58 grams, so 0.058 kilograms. And then the time of the collision I have estimated to be about 0.016 seconds, using the fact that my phone records at 60 frames per second, so it took about a frame to collide, so that's going to be about 0.016 seconds. I've assumed that the ball can be treated as a particle. I've assumed that gravity is negative 9.81 meters per second squared, and that's constant. And I've assumed that there's no air resistance from the low velocity, and also that the dropped velocity is 0, because I didn't throw it down, I just dropped it. And then I'm going to determine the average force on the ball during the collision. Equations that I'm going to use are potential energy is mgh, kinetic energy is 1/2 mv squared, and that's the conservation of momentum equation, mv1 plus the integral of force with respect to time is equal to mv2. So the first thing I've done is solve for the velocity before it collides with the ground. And to do that, I've just set my height, or the potential energy of the ball at my height, equal to the velocity before it hits the ground. And solving for velocity 1, we get that value is equal to 5.86 meters per second down, or negative 5.86 meters per second. And then for h2, knowing that all of the energy after it bounces up must be converted into potential energy, we can set those two energies equal to each other and solve for the velocity as it leaves the ground, and that's going to be 3.80 meters per second up. Now, using the conservation of momentum, we can say that the mass of the tennis ball multiplied by the velocity right before it hits the ground plus the force, or the integral of force with respect to time, is equal to the mass of the ball afterwards, which is the same, and the velocity afterwards, which is 3.8 meters per second. We solve for the average force, and we plug in the values here, and we see that the average force on the ball during this collision is 35.02 newtons.